7.2 Chaos and the damped driven pendulum. Previously, for small oscillations, the pendulum oscillator was approximated as the classic spring oscillator linear restoring force, where the differential equation describing forced oscillation with damping was real form. See equation 7-4, for which we found the solutions. See equation 7-5, where see equation 7-6. If we don't use the small angle approximation to make sin x approximately equals x, and we assume the pendulum wire is stiff, so a pendulum rod, we then have
see equation 7-7. Let's now consider this along the lines of the study done by reference 34. First, let's change variables and overall normalize such that omega equals 1. See equation 7-8. Using the notation of reference 34, we have omega equals theta, not to be confused with the prior omega, to get three independent first-order equations. 1. Omega equals negative omega divided by q minus sine theta plus alpha times cos phi, where q is the quality factor. 2. Theta equals omega. 3. Phi equals gamma. At this point, we've met the two general conditions for there to exist solution domains that are chaotic.
1. The system has three or more dynamical variables. 2. The equations of motion contain nonlinear coupling terms. For our problem, condition 2 is met with the coupling terms sin theta and alpha times cos phi. From reference 34, for the case where q equals 2, we get the following behavior as we increase the driving amplitude alpha. 1. Alpha equals 0.5. The moderately driven pendulum, with simple pendulum-type periodic behavior, once it's settled into a steady state, the trajectory is a limit cycle, thus asymptotically a cycle like with a simple pendulum. 2. Alpha equals 1.07. The pendulum with a double-loop trajectory in its phase diagram, but with the oddity that its trajectory in a configuration diagram has yet to complete one loop even though swings exceeding 180 degrees can occur. 3. Alpha equals 1.15. The pendulum motion has no steady state. It is chaotic. However, its phase diagram indicates structure that is best revealed in terms of a Poincaré section, which track position at multiples of the period of the forcing oscillation. For chaotic motion, the structure of the Poincaré sections, phase space trajectories, is self-similar. This allows a precise fractal dimension to be determined for the chaotic motion. 4. Alpha equals 1.35. The pendulum now completes a loop in configuration, real space. 5. Alpha equals 1.45. The pendulum now completes two loops in configuration, real space. 6. Alpha equals 1.50. The pendulum motion is chaotic.
How to interpolate between the above observations? What is the boundary between systems with steady state and those without, chaotic? This is most easily represented in what's known as the bifurcation diagram. See figure 7.2. In the bifurcation diagram, the instantaneous frequencies observed over a range of driving oscillations from alpha equals 1 to alpha equals 1.50 show a clear period doubling behavior that multiplies quickly on approach to a domain of chaos. Details to follow. Figure 7.2. Bifurcation diagram for a logistic map x sub n plus 1 equals r x sub n times 1 minus x sub n. The bifurcation diagram most clearly captures the transition from system behavior that has steady state to behavior that is chaotic. The previous pendulum system is ubiquitous, but generating precise numerical results with it is time-consuming if all that is wanted is to demonstrate the universal behavior of chaotic systems. This is because the period doubling transition to chaos is a distinctive trait of both second-order dynamical systems and first-order dynamical systems whose iterative mappings, Poincaré sections, involve functions of prior mapping positions that have a simple maxima. General conditions for when a dynamical system with specific mapping dependency gives rise to chaotic behavior has been proven by reference 19 with universal constants also thereby revealed, details to follow. Rather than work with a complex evaluation at each step of the Poincaré section for, say, the pendulum, let's explore the mapping and bifurcation diagram in figure 7.2 that results for the much simpler logistic map, which is first order, but whose key constants are supposedly universal, so easier to evaluate this way. Here is the synopsis from reference 34. By varying the parameter r, the following behavior is observed.
With r between 0 and 1, the population will eventually die, independent of the initial population. With r between 1 and 2, the population will quickly approach the value r1/r, independent of the initial population. With r between 2 and 3, the population will also eventually approach the same value r1/r, but first will fluctuate around that value for some time. The rate of convergence is linear except for r equals 3, when it is dramatically slow, less than linear, see bifurcation memory. With r between 3 and 1 plus the square root of 6 approximately 3.44949, the population will approach permanent oscillations between two values. These two values are dependent on r and given by x_\pm equals \frac 1 to r\left r plus 1 \pm \sqrt r3 r plus 1 \right. With r between 3.44949 and 3.54409, approximately, from almost all initial conditions the population will approach permanent oscillations among four values. The latter number is a root of a 12th degree polynomial, sequence A086181 in the OEIS. With r increasing beyond 3.54409, from almost all initial conditions the population will approach oscillations among 8 values, then 16, 32, etc. The lengths of the parameter intervals that yield oscillations of a given length decrease rapidly. The ratio between the lengths of two successive bifurcation intervals approaches the Feigenbaum constant delta, approximately 4.66920. This behavior is an example of a period doubling cascade. At r approximately 3.56995, sequence A098587 in the OEIS, is the onset of chaos, at the end of the period doubling cascade. From almost all initial conditions, we no longer see oscillations of finite period. Slight variations in the initial population yield dramatically different results over time, a prime characteristic of chaos. Most values of r beyond 3.56995 exhibit chaotic behavior, but there are still certain isolated ranges of r that show non-chaotic behavior. These are sometimes called islands of stability. For instance, beginning at 1 plus the square root of 8, approximately 3.82843, there is a range of parameters r that show oscillation among 3 values, and for slightly higher values of r oscillation among 6 values, then 12, etc.
If the first bifurcation occurs for mu equals mu sub 1, and the second for mu equals mu sub 2, then it is possible to define a universal constant f, after Feigenbaum. See equation 7-9. Where, remarkably, this is a universal behavior for all maps with quadratic maximum. So, in other words, for a simple, real, quadratic map or complex quadratic map, generator of Mandelbrot's set, we arrive at precisely the same constant from their bifurcation maps based on the parameterization of their bifurcation events. Similarly, quadratic maximum map x sub n plus 1 equals a minus x sub n squared has lim over k right arrow infinity of the fraction with numerator a sub k minus a sub k minus 1 and denominator a sub k plus 1 minus a sub k equals f period. Complex quadratic maximum map Mandelbrot z sub n plus 1 equals c plus z sub n squared has lim over k right arrow infinity of the fraction with numerator c sub k minus 1 and denominator c sub k plus 1 minus c sub k equals f period.
7.3 The special value c sub infinity. For the complex quadratic map, the actual asymptote for the c value at the edge of chaos is referred to as c sub infinity and has the value c sub infinity equals negative 1.401155189. The constant, the absolute value of c sub infinity equals 1.401155189. Is also known as Merberg's constant. The Merberg constant, simply called c sub infinity here and in reference 45, will play an important role in discussions. Example 7.1. Let's consider another 1D map that is continuously differentiable with a single maximum on the interval 0, 1 f of x equals a over pi times sine pi x, so that we have the iterative relationship. See equation 7-10. At the first bifurcation point we have. See the next equation.
Let's sketch a plot of the bifurcation diagram revealed by computational results. The values of a where there are the bifurcations indicated are. See the equation shown.
See the next equation. the Feigenbaum number. See equation 7-11. Exercise 7.1. Redo the above analysis for another 1D map that is continuously differentiable with a single maximum on the interval 0, 1.
Example 7.2. Using analytical methods, evaluate period 1, 2 fixed points of the standard map. See the equation shown. Consider the period 1 fixed points where the mapping indicates. See the next equation. While the 1 period indicates r sub 1 equals r sub 0 times a and d times theta sub 1 equals theta sub 0, with angular equality up to a difference of 2m pi. Thus, see the equation shown.
Note that for any solution theta sub 0 equals n pi in the sine function, there is still the solution theta sub 0 equals n pi plus 2m pi from multivaluedness. This is useful to recall in considering solutions to theta sub 1 equals r sub 0 plus theta sub 0. R sub 0 equals 2n pi, not simply r sub 0 equals 0. Thus, the fixed points at period 1 are theta sub 0 equals n pi, r sub 0 equals 2n pi. Let's now consider period 2 fixed points. R sub 2 equals r sub 1 plus epsilon sin theta sub 1 equals r sub 0 plus epsilon sin theta sub 0 plus epsilon the sine of r sub 0 plus theta sub 0 plus epsilon sin theta sub 0. Theta sub 2 equals r sub 1 plus theta sub 1 plus epsilon sin theta sub 1 equals 2 times r sub 0 plus epsilon sin theta sub 0 plus theta sub 0 plus epsilon the sine of r sub 0 plus theta sub 0 plus epsilon sin theta sub 0.
R sub 2 equals r sub 0 right arrow the sine of theta sub 0 plus the sine of r sub 0 plus theta sub 0 plus epsilon sin theta sub 0 equals 0 right arrow theta sub 0 equals n pi times a and d times r sub 0 equals n pi times or times r sub 0 equals 2 n pi. See the next equation. Thus, the fixed points at period 2 are theta sub 0 equals n pi, r sub 0 equals n pi. Let's now consider period 3 fixed points. R sub 3 equals r sub 2 plus epsilon sin theta sub 2 equals r sub 0 plus epsilon sin theta sub 2 plus epsilon sin times r sub 0 plus theta sub 0 plus epsilon sin theta sub 0 plus epsilon sin times open bracket 2 r sub 0 plus theta sub 0 plus epsilon the sine of r sub 0 plus theta sub 0. Close bracket. Once again we have theta sub 0 equals n pi.
See the equation shown. Theta sub 3 equals theta sub 0. See the next equation. Thus, the fixed points at period 3 are theta sub 0 equals n pi, r sub 0 equals 2 n pi. And now the pattern is apparent. Even periods have fixed points at theta sub 0 equals n pi, r sub 0 equals n pi. Odd periods have fixed points at theta sub 0 equals n pi, r sub 0 equals 2 n pi.
Exercise 7.2. Try. See the equation shown.